Prof, I'm going to hand over to you now, bringing you online and also your unmuting you so that you should be able to talk, which would be very good because you need to be able to do this presentation and to be able to see you. So there we go, lights, camera, and action. So I'm now going to hand over to you and also make sure that you can control the mouse so that you can take us through the next presentation. We're really looking forward to it. Over to you, Gunnar.
Thanks very much, Linda. I'm just going to see if my slides work, and thank you for that introduction. Let's see. I don't seem to be able to control the slides.
All good. I'll do it. Not a stress.
Thanks, Linda.
All good.
Right, thank you very much for this opportunity to chat to you about some basic concepts of UV and just go through those and some advantages and shortcomings. As my colleague Peter mentioned, most of the research we've done at Stellenbosch University has been related to the liquid medium. My main area of work is on using UV for water treatment, but the basic principles of how UV works and what the advantages and disadvantages are pretty generic. So just a little bit of background. Ultraviolet light is obviously not actually a light. It's a specific waveform of photons, the much lower wavelengths than our visible light. So we have the region of probably from 100 to 400 nanometers, and the other higher end spectrum above red light is obviously where infrared is. So it's shorter than visible light, but higher than that of X-rays. If you can go to the next slide, please, Linda. So there's maybe a little bit of confusion about the different types of UV that there are, and most of the UV that we're exposed to comes from the sun. So there's UVA in the region of 315 to 400 nanometers, UVB 280 to 315, and then UVC from 100 to 280. And there's also something known as VUV or vacuum UV, which is lower down in the nanometer ranges. Next slide, please. So most of the UV generated by the sun, UVC, doesn't actually reach us. It's UVA and UVB that reaches the Earth's surface, and most of that is the UVA. So it's UVA and UVB that are of main concern for aging and wrinkling and damaging our skin and causing sunburn, which is UVB. So those are not the ones that we are specifically interested in today. Next slide, please. So as Linda mentioned and has been said, we're interested in the region from 200 to 280 nanometers, which is the germicidal range, or UVC, and that's the one that we can use to apply for UV disinfection. The next slide, please. So UV technology is not all that new. I think it's gotten a bit of a bad rap sometimes in certain applications, but it's been around since 1801 when the German physicist Johann Ritter spoke about the effect on silver chloride. Later, another 70 years passed before two Englishmen, Downes and Ballant, published a paper describing the sterilization of bacteria, and they did these experiments in sugar water. And in 1903, Niels Finsen actually received the Nobel Prize for Medicine using UV as a surface disinfectant, but looking specifically at lupus vulgaris, or tuberculosis of the skin. And in water treatment, Marseille in France actually started installing UV disinfection systems in 1910 already for their water drinking, and this was quite common in France as well as in Belgium and also in the Netherlands for quite a long time. It was only in about 1960 that the effect of UV on DNA was established, and we'll get into a little bit more detail as to how that works. By 1985, there was about 1,500 water treatment plants in Europe making use of ultraviolet light. But in 1998, it was discovered that protozoa, Cryptosporidia and Giardia, which are responsible for quite a lot of diarrhea and disease and sickness, especially in developing countries, both are waterborne, quite infectious, and that they are much more vulnerable to UV light, not resistant as much as they are to chlorine, and that's one of the big uses of UV in water treatment. So in Europe and the United States, there's now more than 600 water treatment plants using UV as a disinfection mode. The next slide, please. So UV is effective in altering the chemical structure of certain biological molecules, and specifically the nucleic acids found in DNA, and that's where the main target is. And it's these nucleotide bases, and we all remember our DNA helix, the purines and the pyrimidines, and it's mainly the thymines which are most involved, and we'll get into a little bit of detail to that, but it's changes induced by the UV irradiation to that DNA helix that are responsible for the disinfection by the UV photons. So if we can go to the next slide. So DNA in general has its maximum absorption band at around 260 nanometers, which is quite good because most mercury-based UV lamps have their maximum output or peaks at around 254 nanometers, which makes the action on DNA very good. Proteins also absorb at around 280 nanometers, but at equal concentrations, they are much lower absorbance than the nucleic acids. So it's mainly the action on the DNA rather than on some of the enzymes in cells that is responsible for the disinfection. And the structural alteration is based on the formation of cyclobutane pyrimidine dimers. I know it all sounds very technical, and those are often just called thymine dimers, so thymine being one of those nucleotide bases. And it's normally when these dimers are formed that the DNA structure, when it is unraveled, cannot be replicated, and therefore cells can't reproduce. So if we go into a little bit more detail, it normally happens when two of the thymine bases are adjacent to one another somewhere on their DNA strand, and they then form a linkage with each other, forming this dimer. And when the replication is supposed to happen, that is where the replication terminates, leading to no cell division and therefore the end of multiplication by these bacteria. And that all sounds fantastic, but there are some other mechanisms involved as well, but we'll also get to some of the downsides of those thymine dimers. Some other lesion mechanisms that can be produced are 6,4 photoproducts and their valence isomers. So these can also lead to mutagenesis in the DNA replication, but much less so than the actual thymine dimers. Some other lesions that are initiated can be initiated by alkylating agents, hydrolytic processes, and also the formation of free radicals. But we'll rather focus on the thymine dimers. Unfortunately, a lot of bacterial cells, and as Prof. Gose said, they are clever and they find ways of giving us a hard time. And they have two different mechanisms in which they can possibly repair the damage that has been caused by the UV. And these are either called dark repair or photoreactivation. The one is a nucleotide excision repair, which you can see on the left of this, where a section of the DNA strand is removed, is reconstructed and replaced. That is normally what happens in dark repair, or in enzymatic repair. We have photolyase bacteria, which will attach to the damaged site on the DNA, and through certain enzymatic processes will repair that damage. And I think we can see that in the next slide in a little more detail. So the protein enzyme actually binds to the damaged site where these thymine dimers have been formed, and through a series of enzymatic reactions, that damage is repaired, the thymine dimer bond is broken, and the DNA strand is restored, and therefore replication can take place again. And I'm sure this will be covered in the later applications. It's very dependent on the doses and the type of UV that is used that can minimize the amounts of photo repair or dark repair. So very briefly, if we go into the main advantages of UV disinfection, I'm not going to go into the applications. I'm sure Bastian will elaborate on that. The main advantage of UVC disinfection is it's effective against a whole range of microorganisms and not specific. So algae, bacteria, fungi, molds, nematode eggs, viruses, yeasts, and protozoa specifically, so Cryptosporidium and Giardia. As I've mentioned, those two are very resistant to chlorine disinfection, and therefore a very good example of one of the advantages of UV. Secondly, no chemicals are added to the food or water, which is obviously an advantage. There's also no storage or handling or hazards involved in storing these chemicals. In water specifically, no disinfectant byproducts are formed when organic material is exposed to UV, which is a very big disadvantage. The short contact times, as we know, in cleaning with foams, chemicals, or any other disinfectants, the contact time is very important, so very short exposure times required. Small space requirements, both for UV treatment on water or liquids, but also on conveyor belts or on spaces, can easily be retrofitted as well, which is a great advantage. They're very energy efficient, and I'm sure Bastian will elaborate on that in his presentation, and very user-friendly to use, and it's a lot easier to adjust the dosage, which is also not linear. So in chemical dosing, if you need twice the killing power, you need to add twice the amount of chlorine or whatever disinfectant it is. In UV, it is not quite that linear, which is another example. There are some disadvantages, which we'll see on the next slide. Low doses can be ineffective, but as I've mentioned, getting the incorrect dose is normally just an operator fault. A disadvantage is that UV leaves no residual, but in food applications and in surface, especially when it comes to food surfaces, this is actually an advantage. Obviously, it's a disadvantage in water treatment when we don't have any residual afterwards once the water goes into the distribution system. As we've mentioned, microorganisms can sometimes repair some of this DNA damage, and that needs to be taken into account in the way that we treat them, whether there's follow-up treatments or making sure that we apply a sufficient enough dose to limit that amount of repair. And then obviously food surfaces can deflect UV light, or suspended material in liquid forms can shield microorganisms, so one needs to take that into account. And lastly, lamp breakage gives rise to a mercury hazard, but these safety features are normally built into systems so that these risks are very much minimized. And that really is the short and sweet of an introduction to UV and the limited shortcomings, but the many advantages. I hope that has set the scene and given people a slightly better idea of where UV fits in and what the main mode of action is. And I'm sure we'll see Bastian elaborating quite a lot on those. So thank you very much for listening.
Thanks, Prof. It always just freaks me out that we've got these resurrection bugs. You know, that you think you've done something and then they've got another way around it and they can actually figure it out and they can literally come alive again. It's something that we have to actually pay attention to.
Yeah, it's a big problem that one needs to, and that's where research is so important, because certain bacteria are better at it than others, and possibly combination treatment. Some of the research we've done, where a single dose of UV has been less effective than the same dose applied in 2 separate instances.